Hello everyone, my name is Andrew McLaughlin. I will be presenting my team's research on the gravitational potentials and forces in the lattice universe, a chimney. What is the shape of space? Is the universe infinite or is there a limit to the size of the universe? It could be positively curved, negatively curved, or have zero curvature. General relativity does not favor any particular topology. Therefore, space could be simply connected, or space could be multiply connected. With a multiply connected universe, it could have a finite volume even for negative and zero curvature. In a multiply connected universe, a photon is able to travel multiple times across the volume of space. Possible topologies include three torus, chimney, and slab. There are many studies on the potential indications of the shape of space, which is focused on their relations to the cosmic microwave background data. CMB anomalies and large angular scale observations like the suppression of the quadruple pole moment and the quadruple pole and octopole alignment are imprints of spatial topology. The current data available cannot determine the finiteness of the volume of the universe. For a small volume, it is reasonable to trace observational indications of its shape. Possible topology imprints and CMB observations place constraints on the radius of the largest sphere inscribed in the topological domain. From Planck 2013 data for three possible topologies. The constraints for a flat universe with equal-sided chimney topology, the radius inscribed is greater than 70% of the recombination surface. For chimney topology, in terms of gravitational characteristics of the universe manifested in the shape of the gravitational potential and gravitational forces. The gravitational field is sourced by fluctuations of the matter density. Matter is pressureless and can be considered in the form of discrete point-like gravitating bodies of mass to represent galaxies and co-moving mass density, the equation listed below. Chimney topology, which admits single infinite access subject to the preferred direction of the quadruple pole and octopole alignment and the commonly named axis of evil. Gravitational potential, which is created by fluctuations in matter density, defined by scalar perturbations of metric coefficients as well as satisfying the linearized Einstein's equation, well as ignoring peculiar velocities, the equation is listed below. Working with a shifted potential makes it possible to employ superposition principle in solving the Helmholtz equation. Lambda is the screening length. For chimney topology, Tori 1 has a period L1 along the x-axis, as Tori 2 has a period L2 along the y-axis. For a particle M placed at the center of a Cartesian coordinate for a chimney topology, the delta function of x and y are presented. Peculiar velocities may be effectively restored by employing the effect of screening length. With the effects of peculiar motion restored, the two alternative solutions are listed. The effect of screening length specifies the cutoff distance of gravitational interaction in the cosmological settings. The effect of screening length and the screening length are related at the matter-dominated stage of the universe evolution. The subscript cos and x are used to distinguish between the two solutions. The Yukawa potential. Each term in the series corresponds to the individual contributions of the infinitely many periodic images. A third way to express gravitational potential is with the Yukawa-type interaction which is subject to periodic boundary, can be formulated via Ewald sums and the cosmological set. The expression for the Yukawa-Ewald potential for gravitational potential is listed. For our desired precision for the formula requiring the fewest number of terms to define gravitational potential up to 1/10%, the accuracy is the preferable solution between the gravitational potential of subscript cos and subscript exp. The value of n corresponds to the combined number of sets k1 and k2, which reach the required precision generated in an increase in order of the square root of k1 squared plus k2 squared. In the two charts provided are the values of gravitational potential and the corresponding n values for x, cos, and mixed terms in the series at selected points for the effective screening length of 0.01 and 0.1, which are listed respectively. Due to nx having the least number of terms, the gravitational potential with the x subscript is the preferable solution, being easier to calculate computationally over the gravitational potential with the mixed subscript. Here are the graphs of the rescaled gravitational potential for the effective screening length of 0.01 and 0.1, listed respectively. Gravitational forces along the x and z axis. We omit the y-axis due to the symmetry of x and y. The accuracy of the gravitational forces are like that of gravitational potential. We derive three alternative formulas for the x and z components of the rescaled forces as follows, with the first two listed. Third alternative formula for the x and z component of the rescaled forces is listed. Provided are four charts for the values of the x component, the top two charts, and the z component listed in the bottom two charts of the rescaled gravitational forces corresponding to screening lengths of 0.01 and 0.1. Provided are the graphs for the rescaled x components of the gravitational force for the effective screening length of 0.01 and 0.1 for the sections z equals 0 and y equals 0. Provided are the graphs for the rescaled z component of the gravitational forces for the effective screening length of 0.01 and 0.1. We have examined how chimney topology of the universe affects the form of gravitational potential and of gravitational force. We have proposed three alternative forms of solutions. One by Fourier expansion of delta functions along toroidal dimensions. The second one followed from the direct summation of the solutions of the Helmholtz equation, each in the form of the Yukawa potential, for a scarce particle in all its images. And a third formula is formulated via Ewald sums for Yukawa potential. For both gravitational potentials and forces, the formulas involving direct summations of Yukawa potential present the best case for an effective screen length, which is less than 1. Obtaining the desired accuracy is achieved by keeping as few terms in the series as possible. Thank you everyone for joining us today.